So you're looking a bit glazed. As if we guess. Yes.
Yeah, to help with the glazing, it would help me if we would go back to the big picture.
This big picture?
Yeah.
Okay.
And just go through it little by little, saying what information is available and what gets stripped out. I mean, you've been through all that, but it would just be nice to have you put it back together.
Okay, so let me have a go. You tell me whether I'm answering the question that's in your mind.
Yeah.
Okay, so at this stage, we've just got a syntax tree with these rudder names inside, pretty much strings and module names. Okay. The renamer resolves all the lexical scopes, replacing all those rudder names with names. So it's still in our very big data. There is, I've not described, and I would be one of on the what you'd like to hear more about page. One thing that I've written quite a lot about is how the renamer works. So there's a whole page about that that I won't go through just now, but it's on this it's in this overview compiling one module page.
Where do you put what you want to hear more about things again?
Oh, that's on the hackathon. Right at the top of the hackathon page, there's a link. Right, there's a link right at the top sentence of the hackathon. Okay, type checker type checks this big data type, replacing all the rudder names with IDs. But in addition, it generates, I should have written really at the side here, it also generates a type environment that defines all the tycons and classes corresponding to that come from the program as well. These guys, tycon and class and IDs, they all live in the type environment that come, as it were, along with this whole data type, which is the as yet undesugared program as the type environment. It's generated by the type checker. Yeah,
where can I find binding group analysis?
Binding group analysis? Do you mean where we divide things into strongly connected components? Yeah. Good question. So that the renamer, which has to find the renamer as well as doing the scope resolution, does a number of other tasks that I think I mentioned in that slide. One of the things is finding bindings that are not used, and doing this strongly connected component analysis. So it gathers renamer as it's renaming the program. It generates the free variables of every subterm. When it comes to a binding group, it sorts it into its strongly connected components and puts those. So there's enough structure in the HS binds data type to show that.
Okay, then do you actually also reorder the whole abstract syntax tree? Or?
Just the bindings. So the bindings are reordered, yes. But they still have their source locations attached to them, so that's okay. Then in the type checker, there's a second strongly connected component analysis, because even if two declarations are mutually recursive, one might have a type signature. And so this is Mark Jones pointed this out. I'm sort of folklore. Mark quite explicitly. It's in the typing Haskell paper. So even though F and G are mutually recursive, if F has a type signature, well, type signature in the type environment, type check G. Now generalize that and put that in the type environment and type check F. Right? So for some bizarre reason, the type checker takes the strongly connected components good by the renamer, cuts the links at the type signatures, and does a second strongly connected component analysis to break it up yet still further, right? To do this more refined type checking. So it's sort of split it between the type checker and the renamer. Okay. So then we got to here, it's got abstract syntax and a type environment. Desugarer converts all this into this very small core language. So I've written core expert, but actually the main payload of the program is a list of core bindings, a list of top-level bindings. Right. The type environment is still there, right? So we still keep it. That lives on. It's not desugared in any way. The type environment just stays. Yeah.
Can the core be outputted to somewhere else and re-imported later on?
Yes. So some while ago, Andrew Tolmack went through the exercise of defining an external syntax for core. It's called external core. So by saying -f hyphen core, GHC will print actually at this stage. It will print out the program in this externally parsable core syntax form. I fear that not enough people. I don't know who. It doesn't really have an owner at the moment, is the trouble, and not many people have complained about it. So I suspect that it's bit-rotted. One of the things about GHC is that sometimes we tend to pay attention to what people complain about. I suspect there's people who try to use external core, find it sort of bit-rotted bit and given up. So actually it's kind of looking for an owner, because it's quite a convenient thing to be able to dump it out as external core, right? Munge on it a bit, and then read it back in. And GHC does have a way to read back in external core, rename it and type check it. That whole route kind of exists, but it's sort of, I think it's, I'm not sure it'll work with FC, for example, or that GADTs are fully there. But essentially, external core hasn't kept up with the rest of the compiler. But in principle, yes. Or the other thing is, of course, if you're using GHC as a library, you should just be able to get hold of the core program. I'm not sure that we can today. You should be able to get hold of the core program and beat on it and stuff it back in. But again, that API probably doesn't exist today, but it should. That certainly is the intention. It should be possible today. Yeah, I know. So I can't hear.
Pattern matching compilation?
Yes. Pattern matching compilation, when you take nested patterns and turn them into matching on flat patterns, is done by the desugarer. Yes. So the type checker has type checked patterns in their fully nested form and has not transformed them at all. It just leaves them exactly the way they were. Remember? So there's no systematic change of structure here. The desugarer does the pattern matching compilation. Now there's a slight tension here, because actually checking for exhaustiveness in pattern matching uses GADT kind of information as well if you're really going to do a good job. And so the exhaustiveness checker is in the desugarer. It's a bit weird. It was written by a student quite a long time ago, and it needs rewriting. But it's not quite obvious to me how to take advantage of the type check information, but it certainly should be possible. So there's another project: is make the exhaustive pattern matching checking not only make it work properly, but make it cognizant of GADTs. But anyway, it's done here. Actually, in some ways, it's overkill. The thing that's done here is pretty much pattern matching compilation as described in my 1987 book in the chapters with Phil Wadlow. And it tries to generate a reasonably efficient program, like one that if you say f of x is true equals something, and then f of x is false equals something else, then the pattern matching compiler says, oh, I see, you're doing this in a block, and we just do one pattern match. But actually, if you did the completely naive left to right, top to bottom compilation, and then fed it to the simplifier, I think you get the same answer. In the code, there's no fat bar. That's perfectly true. So how does failure work? How do you? No. So the way that failure in pattern matching is done is this: that if you've got two. Let's see how to say this. Yes, f of just b equals f of a b or something else, right? So here, if this fails, you want to go to this right-hand side, and if this fails, you also want to go to this right-hand side. So the way we do that is just with the same join point mechanism, right? So we'll say let fail. This is just an ordinary identifier equal. Well, now this is all in the lambda PQ. So that's the original arguments to f. You now would say let a equals p and b equals q in, which we call this R2. In. And now we'll do this stuff, right? Case p of just a arrow. Now we'll do something. But if it's nothing, then we just get fail. So there's no fat bar. It's just this ordinary identifier. And it turns into a let no escape thing. Unless it's small and it gets, one of the advantages of this way of handling join points is that if this was turned out to be very small, even if it's used several times, it might be just copied because the simplifier will say, oh, small piece of code, right, copy it. If it turns out to only be used once, actually, it'll be inlined. Right? So good things happen. That's the way that what was called fat farming in the book works instead. Right. So I'm sort of popping the stats back to your original question. Right? We're doing okay up to here. Okay. So now now we've got the program in the form of a list of bindings. And just repeatedly transform, optimize, analyze. It still stays as a list of bindings. List of core expression bindings in this small data type. We do some of this post-processing, which I think there's a quick summary of each of these, and actually the core tidy module and the core prep module both have pretty good comments at the top that explain what tasks they do. Each of them has several tasks to do. And now I convert to this STG syntax thing, which is just a decorated form of a normal formalized core. And feed it. But I feel like I haven't answered all that was in your mind. Well,
I'm not certain what was in my mind.
right.
I think I just wanted a review of where everything was, and the auxiliary questions were helpful in just
Yeah, great.
where every page goes.
Right. Yeah.
Where is all different pieces of simplify in the source tree?
Oh, in a directory called simple core.
Okay.
Compiler simple core contains most of these, not specialized. Specializing is in compiler specialize.
Okay.
But all this left floating stuff. Oh, and strictness analysis is in compiler rationale. Right. So I should add these to the.
I think it would be very useful if you tag each one of these stages with the files associated with them.
Right. So where are we? I should do that right here. Right. So I added some papers, but I should point to which directories and so forth. This list would be the obvious place to do it. Yes. Yeah.
Can you give a reference about system FC?
Oh yes, FC. It's on my homepage, and it's called. The paper is called what's called System F with Equality Coercions. Rejected by ICFP 2006. Rejected by Popple 2007.
That's right, CFP 07.
That's right. That's a long way off. We're going for the grand slam of rejected by PLDI first. Well, either that, we'll have to.
Time with PLDI.
It's clearly a difficult. It's not an easy sell. This paper. Actually, I'm quite proud of this paper. So I'd be interested. Let me encourage you to read it, and help me to find a way to explain why it is so good. Maybe I'm clearly rather biased, but it's a paper. I feel as if it was a little breakthrough, and it's fully implemented in this FC2 branch. It's the way GHC works. Yeah.
In the early days when you're building GHC initially,
Yeah.
which order did you start building the parts within that pipeline?
Oh, when we were originally building it, I think.
Like once you start getting towards the pipeline looking like the way it is?
Yes, it was. Yes, so we still had the big data type.
Mm-hmm.
I think the renamer, in fact, I remember when I was on sabbatical at OGI in Portland in 1996, 7 or 7, 8? 96. That was the time when I wrote the new iteration of the renamer that is essentially the one that we now have. We had a sort of so it took a bit of evolution to figure out there was exactly something called a renamer, to figure out just what it did. And then, so that's been there, I suppose, for nearly nine years now. The type checker was certainly in the same place all the time. The core language has evolved, but even in the initial days, it was essentially System F plus data types. And the back-end stuff has changed quite a bit. It's been rewritten at least a couple of times. So the overall shape hasn't changed all that much. Lots of the details have like that. The way that interface files are generated, the details of that have changed frequently. But the place that they come out and their purpose hasn't changed at all. Yeah.
At some point, when you're moving away from core, and I'm not clear how much of this happens in STG, but at some point you need to know things like the layout of heap objects. You need to start manipulating allocation pointers explicitly.
Yeah.
You need to have the layout of the stack and start manipulating
Good.
stack pointer explicitly. Where did those things start to happen?
They have in the code generator. So SDG is still, as described by that paper about compiling language from stock hardware. SDG is still pretty abstract. It does not say which word lives in which location. It still looks like sort of lambda code of a very particular form. The code generator does all the things you're describing. It fixes the layout of, fixes exactly where every word is. It fixes the exact layout of the stack and which registers are used to pass arguments. It should be factored a bit, as we frequently discuss. The code generator, I'd like to factor it into two, one of which uses C++ native calls, and the other, and therefore leaves the business of stack layout to C++, and a second phase which makes the stack layout explicit, which would be which you could eliminate if you were going to a C++ compiler. They haven't done that. So at the moment, the code generator has a lot to do.
So when you look at STG, can you just tell where it's going to allocate? Or
Oh yes.
So, okay.
In STG, let allocates. Period.
Okay.
Let no escape, does a little save and allocation. Case pushes a return address and jumps. So there's a very strong operational intuition for every STG thing, which is not quite. There's a still strong but a bit weaker version of the same thing for calls. For example, you can't tell what a let no escape is. But with STG, it's very, very strong. So the place to start looking when you're debugging code and you're figuring out what's going on, always start looking at the STG code, and then now you need to know the exact layout of the object that you're peering at in the heap. Now you have to look at the HC file that's generated. But the STG code is your guide. And the labels in the generated machine code come from the STG labels. So if there's a local declaration of just a purely local value like this guy, he will have a unique like F767 somewhere, and that will be the one that's used in the generated machine code. So you can go back from the generated code to the STG pretty exactly, whereas that's not true for call.
The FC2 branch is the head branch?
Not yet. So we delayed making it the head branch just so that we could have this workshop without messing you all up. So the FC2 branch at the moment is a branch. It's in a repository called GHC FC2.
So in order to get it will be through doors.
Oh, you can get it today by just saying docs at Haskell.org GHC FC2. But as of about a week's time, as soon as we push this compiler, you'll get the FC2 branch. And that will have these lovely index type families and associated types. It's also cool.
What's the name of the paper?
It's called System F with equality coefficients.
Okay. Type equality.
Type equality. System F with type
I'm
equality.
reading it.
Yeah. Great. Yes.
Just show which.
No longer used.
Oh, at what point is type information no longer used? Type information is preserved absolutely up to here.
But so it's still being manipulated by course idea.
Every pass here maintains type information. Core lint will work on the result of core grab. Right? Type abstractions, type applications, the whole, like when you manipulate a type program, it sort of fits together like a jigsaw puzzle. You transform it and you must explain in effect by giving all the types and abstractions and applications why it is still well typed. That holds all the way down to here. So that obligates every pass to make sure that if it's going to do a transformation, it adds all the type information that's necessary. In this stage to STG, it's this information is largely thrown away, not entirely. Essentially, the monomorphic type constructor information is still there. So if you're doing a case on a list, the STG case says this is a case on the list thing, so I'll do a vectored return. But it doesn't say list of pairs of trees and this and that. And certainly polymorphism information is not returned. It could be. So we could have a sort of typed STG language, but we just never have. So that's as far as it goes. And it's preserved right the way here. So in the HI file, you'll have effectively a serialized form of the bindings, at least the smaller bindings, functions in the module, so that other modules, when they're compiled, can read the HI files and take advantage of the actual core language definitions of functions defined in module F. So that's how cross-module inline works.
So it's really polymorphism is no longer used even in concrete. Or it is.
Polymorphism, well, it's preserved. I don't know what you mean by used. So up to here, you can still run limit. So all the polymorphism is still there. And this step is when it's discarded.